Hi guys, today's video I'm going to focus on Newton's laws. So today we're going to look at the first two laws, and as you'll see in a second, those two laws sort of go hand in hand. So we'll talk about both of those together, and we'll actually look at one problem which involves both of those laws. So the first thing we want to do here is we want to ask, what do those laws say? So we'll start with the first law, and what the first law says in words is that if an object experiences no external net force, so that means if you add up all the forces acting on an object and it equals to 0, then that object will move with either constant velocity or 0 velocity, and therefore it's going to have no acceleration. So in symbols, we can write this out over here, which is to say our first law, I'll write this as number 1, is sum. So this right here, this is called a sigma, and that just means we're going to add up all of the forces. So this just says add up every force that's acting on the object, and we're saying if that is equal to 0, then there's no acceleration. So when the sum of the forces is equal to 0, there's no acceleration. If the object is moving at constant velocity, it will remain at constant velocity. And if it's not moving at all, so if it's at rest, it'll remain at rest. So this is nice, but it really actually doesn't tell us a whole lot because, of course, the word here we use is force, and we don't actually have a precise definition of what a force is yet. So at the moment, all this really tells us is that an object will keep moving insofar as it keeps moving. We sort of need to define what does a force mean, what would actually stop an object from moving, or what would change an object's acceleration. And so that comes in the second law. So the second law really just gives us this idea that if we have a net or a sum force on an object, then it will accelerate, and it will accelerate with the relationship that the sum of the forces, so again, whatever the total net force on the object is going to be equal to the mass times the acceleration. And again, these are both of the object that we're looking at. So this is basically just saying, here are our first two laws, and now you see that they're almost really, both manifestations of the same thing. They both come from this idea here, which is that our net force is going to equal to our mass times our acceleration. So if the object is moving with a constant velocity, this acceleration is 0, and then we sort of just break down into the first law, which told us just that if the object is not moving with an acceleration, it must not have any force acting on it. So here are our first two laws, and I think to a lot of students this seems very natural to start, and it seems like it's almost obvious. But we really want to see here, this was actually a big conceptual shift in terms of science. So before this came along, before Newtonian mechanics was big, we had what was called Aristotelian mechanics, which basically said that every object has a natural resting place, and that is at rest. So the idea there, which this shifted away from, was the idea that an object is most happy at rest. And so what we have here is fundamentally different, and it's a viewpoint that you guys are going to want to take during this class, which is to say an object at rest is happy, but is also just as happy being in some constant velocity motion. So you see with the first law again, if an object is moving with constant velocity or if it's at rest, it's equally happy in both of those states. And so when we think of the world, of course, most things, if you see a ball rolling or anything like that, most of these things do tend to come to a rest, but really that will often be some sort of a frictional force that is causing that to happen. So we want to remember fundamentally, while there are frictional forces, fundamentally what's really happening is if it's moving at a constant velocity, it's happy moving at that velocity, and it won't stop until another force is exerted on it. Okay, so now that we have some brief understanding here, let's apply these and let's iron out some of the details with the problem. So the problem statement for today is as follows. An 1,130 kilogram car is held in place by a light cable on a frictionless ramp, as seen in the diagram below. The cable makes an angle of 31 degrees with the ramp, which itself makes an angle of 25 degrees with the ground. And then the problem asks us to A, find the tension of the cable and the normal force of the car, and then B, the cable is suddenly cut. What acceleration does the car now experience? Okay, so now that we've read out our problem, we want to look at the diagram of what's going on. So I'm going to draw that out over here. And so I'm going to draw our ramp right here. And we're told that the ramp is at an angle of 25 degrees from the ground. And then this box will be our car, which is held up by a cable, which is at an angle of 31 degrees with respect to the surface of the ramp. So this is really the picture of what's going on, but what we want to use for these force problems is we're going to want to look at what's called a free body diagram. So this will be much more useful than this general picture, which is to say I'm going to redraw the object, which is the car, and I'm just going to focus only entirely on the forces acting on the object itself. So I'm going to focus on the three forces we have here. So one of those is the gravitational force, which pulls this car downwards. One of those is going to be what's called the tension force. So this is just the force that the cable exerts on the car. And then one of these will be what is called a normal force. And so our normal force is just saying that the car is not going to be falling through the ramp, so the ramp must therefore be exerting some force so that the car doesn't go through it. So that's going to be called the normal force. So this here is our free body diagram. And so once we have that set up, we now need to decide on a coordinate system. So we see there's a couple of angles. There's actually two separate angles here. So we're going to have to worry about some components. So we want to first pin down our coordinate system. So I'm going to choose over here on the diagram our x to be along the surface and our y to be perpendicular to the surface. So now that we have this chosen, what we want to do is we want to look at each of the components of these vectors along the x direction and along the y direction, and then we're going to look at those separately. So the idea here is going to be that we see the car is in equilibrium, so it's obeying Newton's first law, which says that the sum of the forces must be equal to 0 in order for there to be no acceleration on the car. And so if that's the case, we want to look at both the x direction and the y direction, and we know in each of those directions the sum of the forces must be 0. So the sum of the forces in the x must be 0, the sum of the forces in the y must be 0 as well. So the first step is, as I said, to split this up into coordinates. So let's look at the coordinates of the gravitational force first, and so I'm going to split that up and draw the y coordinate, which we'll call FGY, in green, and then we will draw the x coordinate FGX in red. So we'll do the same thing for the tension. Again, the gravitational force and the tension we see are not directly along either, so we have to split up into the components. So for the tension, I am going to draw this right here is our F tension in the y, and then our F tension in the x. So we see what we get here is we get sort of two nice right triangles. And this sort of means that once we can get the angles of these triangles, we can use some trigonometry and really solve for all of these components. And that's going to be something you'll do almost every time. Anytime you have an angle in these force problems, you want to directly split it up into its components along x and along y, and then use these triangles to figure out what those are. So one thing we know right away is that this angle here is 31 degrees. So we can just see from our diagram at the beginning, that angle is 31 degrees. This angle right here, we actually don't know. So this one right here, we're not quite sure yet because we only have that this angle is 25 between the ramp and the ground, but we're not sure how that's related yet. So let's step over here to the diagram and let's sort of use a little bit of geometry and figure out exactly what the angle that the gravitational vector makes is. So I'm just going to redraw that gravitational vector here, and I'll draw this triangle. So this is the triangle we're concerned with. And so again, we want this angle. So if we look at this diagram, we see right here we have a triangle. So this triangle right here, we see that it's a right triangle. So this here is 90 degrees. And therefore, this angle up here must be equal to 65 degrees. That's just to say all of these angles must add to 180. So that must be 65. So then one more step and we can get to our angle, which is just to say this angle here is 90 degrees. So these two must add to 90, and so that must be 25. So make sure you follow all of those steps. This will come up again and again, but it turns out that this angle is actually just the same as the angle of the ramp with respect to the ground. So now we have our triangle set up. We have sort of all the components where we want them to be. So let's just go ahead and write down explicitly what all of these components will come out to then. So we will have that the magnitude of the force tension in the y. So I'm just going to write the magnitude now. I'm not worried about directions yet. But the magnitude we know from this triangle here is just going to be, through trigonometry, force of tension in the y times sine of 31 degrees. And so then similarly, we'll do the same for the x. And so again, this is something you can follow along in the solutions in a bit more detail. But ideally, this is just straight from trigonometry. So this should be times cosine of 31 degrees. So we'll do the same thing for the gravitational force. So again, now we want force of gravitation in the y. And so if we look at that, this should just be force of gravity times cosine of 25 degrees. And then similarly, force of gravity in the x we can get, and that should just be the force of gravity times sine of 25 degrees. Okay, so now that we have our components here, we have really a lot of information about our problem. And at this point, we just need to apply Newton's first law, and we can actually get to our first two answers for part A. So for part A, what we want to do is remember, again, this is in equilibrium. So that means that the sum of the forces, so as we said, in the beginning of the video, the sum of the forces must be 0 in order for this to be at rest. So this is going to happen in both the x and in the y. So let's make this explicit. Both in the x and in the y, the sum of the forces must be 0. So first, let's look at the x direction. We see that the sum of the forces in the x, we have two. We have the force of tension in the x, and we have the force of gravity in the x. And they're going in different directions. So let's remember, the x direction positive is up the ramp. So that means that F tension in the x direction is a positive. And we're going to want to subtract off our F of gravity, of gravity in the x direction. So that's just saying the force of tension in the x is pointing in the positive direction. F gravity in the y is actually going to be a negative value. But other than that, we're just going to read down here, and we're going to plug in and set these equal to 0. So you could follow along in the solutions, but doing this, you should be able to solve through and get that your tension force is equal to 5460 newtons. So again, we've just taken each of these values from down here, and really we can, if we want to be a little bit more explicit, these are the magnitudes. So I've included the direction with the minus sign. And then we could do the same thing for the y direction. So in the y direction, we see we actually have three forces. We have the normal force, the component of the tension force in the y, and the component of the gravitational force. So if we do this, we see that our normal force is going to be in the positive direction. So is our tension force in the y. And then we're going to have to subtract off the gravitational force because that is in our negative direction. So Fgy. And that all equals to 0. So again, we can plug in the things we have down here, and we should be able to solve through, and you should get that your normal force comes out to be 7220 newtons. So that is our answer for our normal and our tension. So that's just to say the tension force in the cable for this to be in equilibrium must be 5460 newtons. The normal force on the car must be 7220 newtons. So that's part A. So now let's move on to part B, which asks us if the cable is cut, what must the acceleration be? So what happens when the cable is cut is that this force goes away, and therefore really all of this information, all of the force of the tension is going to totally disappear. And so in that case, we see that the force in the y direction won't necessarily change, which is good because we don't expect if we cut the cord for this car to sort of accelerate away from the ramp or towards the ramp. But what will happen is the car is going to accelerate downwards in the ramp. So it's going to accelerate in the x direction. So we can write from the second law, the sum of the forces in the x must be equal to the mass times the acceleration in the x. So this is just a relation we know between force and acceleration. And then we see in the x direction, once the cable's cut, we only have one force acting, and that is Fgx. So what we really get here is we see this Fgx is in the negative direction. So we basically just have negative times the magnitude of the force of gravity in the x must be equal to mass times acceleration. So again, they ask for acceleration, so we can just divide through by mass. We have our Fgx defined down here. And again, Fg is going to be mass times gravity, so we can plug that straight in. And once we do all of the above, we should be able to solve through for our acceleration, which we should get as 4.14 meters per second squared. So that's to say once we cut the cable, it's going to accelerate down the ramp with an acceleration of 4.14 meters per second squared. Okay, so now let's quickly review what we've just done. So we first drew a picture of what was going on, and then we drew a free body diagram and chose our coordinate system for each of these. From this, we saw that we needed to break down each of the force into its components along the x and the y directions, which we used some trigonometry to find. Then we noted that the car was in equilibrium, so the sum of the forces along each axis had to be set to 0. That's Newton's first law. So doing that, we were able to solve for the tension and the normal force. And then finally, when the cord was cut, we realized that it was no longer in equilibrium. And so the only force acting in the x direction was the component of the gravitational force. So we used the second law in the x direction, the sum of the forces is equal to ma, to find that acceleration. All right, so I hope you guys learned a little something about Newton's first two laws, and particularly how to apply them to a real-world scenario. So if you guys have any comments on any of these videos, please post those under the Videos tab on TED. There should be a survey that you can complete. Thanks for watching.